Hello, dear students. I am Samir Velankar and I welcome all of you to this first video on the topic AVL search tree or AVL tree. Now, AVL is named after its discoverers, Adelson-Velsky and Landis-tree. So, these are the scientists, computer scientists who created this tree. Actually, the good news is that AVL tree is nothing but binary search tree. And you already know what is binary search tree. You know the ordering less than greater than. You know the node structure. So it is nothing but binary search tree, but it is balanced. This binary search balanced. So we really don't have to understand what is binary search tree. That is known by us. What we have to know is what do you mean by balanced here? This word. We are going to spend some 5 minutes in understanding the word. What do you mean by balanced? Now you see the definition is AVL tree is a self-balancing, that is balanced, binary search tree. AVL tree is a binary search tree, but it is balanced, where the difference between heights or depth, whatever you say, height or depth, both words are same. Difference between heights of left and right subtrees cannot be more than one for all the. This formula can be written as absolute value of HL minus HR can be less than or equal to 1 for all nodes. Where HL I have written in the absolute value is height of left subtree and HR I have written is height of right subtree. But we take the absolute value of the difference between the two heights and compare it with 1. Just as an example, you just check this. Suppose I am having a binary search tree, This is the binary search tree I am having. Let's say the values are 10, 5. Now, if I ask you what is the left height of node 5, then left height of this node 5, left height is 1, because the number of levels that you see at the left of 5, number of levels that you see at the left of 5 is just one level. Now, suppose there is one more node to the right of 2. Just imagine. This is 3. This is the binary search tree now. And if I ask you what is the left height of this node 5, what is the left height? Now, left height of this node 5 will be 2, because if you see this left branch of 5, if you see left branch, there are 2 levels. This is one level and this is another level which I am marking. So you can see how deeper can you go in this left height is 2. So the left height of 5 is going to be 2. What is right height of 5? Now you can see that the right pointer of 5 is null. So the right height of 5 is 0. Okay, just see. What is the left height of 10? 10 is the root. What is the left height? If you take this left branch of 10, how many levels deeper you can? You have this level which I am marking, first level, the next level which I am now marking, and the next level. So I can go 3 levels deeper. So the left height, if you go towards the left of 10, you can go 3 levels deeper. So the left height of 10 is going to be 3. What about right height of 10? Well, right height of 10, you can see if you take the right path of 10, then you have only one level, that is where 20 is. So the right height of 10 is just 1. Okay, let's revise this. Suppose I have a tree like this. Oh, I'm so sorry for this. Suppose I have a tree like this. Okay, and some values like 10, 8, 5, 2, and this can be 7. This is 20. Hmm? Now, if I ask you what is the left height of 10, what is the left height? Now, left height of 10 is this level 1, then level 2, then level 3, isn't it? See, at this level 3, both nodes 2 and 7 are there. So the left height of 10 is 3, and right height of 10 is just 1, because only this node 20 is there at this level. There is nothing deeper than this 20. So the right height is 1, left height is 3. If I add one more node here, the right of 8, suppose. What is the left height of 10? It is still 3, isn't it? So please try to understand, by finding height doesn't mean that we are counting the number of nodes on the left. We just have to know how deep we can go in the tree as far as levels are concerned. And towards the left of 10, now still you have one level, second level, and third level. So the left height of 10 is 3, and the right height of 10 in this tree is 1. So coming back to the definition we wrote is that for any node, absolute value of HL minus HR, absolute value of these differences between the heights of left and heights of right, be less than or equal to 1. It cannot be greater than 1. So again, let's consider some examples. Suppose I have a tree like this, very small tree. This is the binary search tree. Yeah, it is a binary search tree because less than, greater than rules are preserved. Now, is this tree balanced? Is this a balanced binary search tree? Yes, it is balanced because every node in this binary search tree obeys the rule that difference between the left height and right height can be at the most 1. Now, I am telling you the best way to check whether the tree is balanced or not is to check every node from the bottom. I repeat, somebody gives you a binary search tree and asks you, check, is this binary search tree balanced? Then the best way to check whether the binary search tree is balanced or not is to see all the nodes from the bottom level, and then go towards the top, checking whether any node is there which is disobeying the rule, or the node for which the difference between the heights is greater than 1. So if you see this tree from the bottom level, the small tree that I have drawn, from the bottom level, phi is balanced. Why really phi is balanced? Because what is the left height of phi? 0. There is nothing to the left of phi. And what is right height of phi? 0. Because there is nothing to the right of phi. So what is the difference between the heights for this node phi? 0. 0 minus 0. Correct? And 0, the difference between the left height and right height, that is 0, is less than 1. So the rule that I was saying, the difference between the heights should be less than or equal to 1, is obeyed. Similarly, difference between left height and right height of 20, check this 20, is a leaf node. Difference between the heights is 0 again, 0 minus 0. And what is the difference between the left height and right height of 10? Now you see, after checking this lowest level, we have gone on top and we are checking node at the higher level. Is this also obeying the rule? Is 10 also obeying the rule? Yes, it is obeying the rule because the difference between the left height and right height is 0 minus 0. See, sorry, 1 minus 1. I'm so sorry. What is the height of left for 10? 1, because there is only one level on the left. And what is the height of right of 10? It is again 1, because there is only one level. So it is 1 minus 1, that is 0. So 10 is also having heights in such a way that difference between the heights is not more than 1. Then this tree is balanced. Because all the nodes in this tree, all three, are obeying the rule. Okay, I'll extend the tree a bit. Now imagine that the tree given over here is, I add one more node. Suppose to the left of 5, I have to this tree now. Now, is this tree balanced? Yes, it is still balanced. You know what? Any student who starts learning AVL tree would initially think that means all leaves are at same level, because possibly by the time student reaches AVL tree discussion, he or she has already learned B and B plus tree. And we know balanced tree means all leaves are at same level. One might feel that 2 is a leaf and 20 is a leaf, but both leaves are not at same level, isn't it? So this is unbalanced. Okay, but this is balanced tree. How do you check it? Whether the tree is balanced or not, you better start from the lowest level. Always start from the lowest level and check to the lowest node. The difference between left and right for 2 is 0, correct? Because height of left is 0 and height of right is 0. Now, once you check this 2 at the lowest level, no other nodes at the lowest level now. So you go at the upper level now, where 5 and 20 are stored, and you check 5. You ask 5 about the difference between the left and right. Now, left height of 5, as you observe, is 1, because there is one level at the left of 5, which is 2, and right height of 5, right height is 0. So the difference between right height of 5 is 1, correct? 1 minus 0. And 1 is allowed according to our difference between the heights can be 1 or less than 1, but it cannot be more than 1. So 5 is also obeying the rule. 20 is perfectly obeying, because left height and right height of 20 is 0. So 0 minus 0 is 0, which is allowed. And now when you finally come to root node, which is storing 10, see this, the root node here is having left height. Check the left height. Left height of 10 is 2, because there are two levels deep on the left of 10, and the right height of 10 is just 1. So the difference between the left height and right height of 10 is 2 minus 1, which is 1. So 10 is also obeying the rule, because difference between their heights is not crossing 1. So all the nodes in this tree are obeying the rule. Hence, the tree is balanced, isn't it? Now, let's take one more or a very simple example, and you just try to answer, is this tree balanced? I'm drawing some arbitrary tree now. Let's say that we have a tree like this. Okay, now is this tree balanced? Now, nothing complicated in this. If we patiently check every node from the bottom and then go upwards and then check whether the every node is following the rule, that is, the rule is absolute value of HL minus HR should be less than or equal to 1. So if you start from bottommost level, this which I am ticking is balanced, because the height of left is 0, height of right is 0, difference is 0. This node is also balanced, coming one level up now, because left height is 1, as you see, and right height is 0. So the difference is 1. Coming to the next node at the same level, the node is balanced 0 minus 0, which is perfectly balanced, you see. And the next node at the same level is also balanced 0 minus 0, left height, right height. Now let's come one level up. Now the node which I am ticking is also balanced because the left height of this node, if you observe, is 2. I am not now marking that horizontal line for explaining the levels, but you can understand that the left of this node, which I am right now pointing to, is there are 2 levels deep on the left, and the right is 1. Right is 1. So 2 minus 1. 1 is the difference of left height and right height. Similarly, the companion or peer of this node at the same level is also balanced. Check the height of left. Height of left here is 0, and height of right here is 1. Height of left is 0, height of right is 1. So absolute value of 0 minus 1 should be less than or equal to 1. And absolute value of minus 1, as you see, is 1, which is less than or equal to 1. I hope you have understood now why we take absolute value. Because while finding difference between left height and right height, it might happen that left height is less than right height. So we might get a negative value. Okay. So now let's come to root. Finally, all nodes at the bottom level are obeying the rule. What if we check the root node? What is the left height of root? Left height of root, if you see this branch, left height is 3. Is 3, isn't it? You can see the levels that we can go deeper here is 1, 2, and 3. Left height is clearly 3, and right height of this root is 2. We can go 2 levels deeper. So 3 minus 2, left height is 3 and right height is 2. Difference is 1, which is perfect. So this is a balanced tree. I hope you're understanding what you mean by balanced. Now let's take an example and check whether this tree is balanced or not. Very fast we will do this. Okay. Suppose we have a tree like this. This is the tree. Let's check from bottom level. This is balanced. I am ticking 0 minus 0. This is balanced 1, 1 minus 0, isn't it? Balanced. This is balanced at the same level 0 minus 0. Allowed. Now let's check this node which I am marking right now. This node. The left height is 2. You can see that left height is 2 and right height is 1. Right height of this node is 1. So 2 minus 1, 1 allowed. Now you can see the node here is also balanced because 0 minus 0 is allowed. But now if you check the root node. Root node has the left height 3. Check, there are 3 levels to the left of root, just 1 level to the right of root. So 3 minus 1 is 2. Not allowed, isn't it? Not allowed. So this tree is unbalanced. Correct? Now, besides knowing that tree is unbalanced, carefully, you should also know which node is not. The node which is not balanced in the above example is root node. Because from the bottom, we checked every node. From the bottom of the tree, we checked every node. And the first node from the bottom, which was disobeying the rule, was root. So you should know that the tree is unbalanced, and you should also know which node from the bottom is the first node which is disobeying the rule. In this example, root node is disobeying the rule. Okay, check this tree now. I will come to the trees which I have drawn there in the slide. You might be thinking why sir has drawn all this. By the way, suppose we have a tree like this. Let's say this is the tree we are having. Okay. Now is this tree balanced? Check from the bottommost level. Perfectly balanced. 0 minus 0. up by one level. This node is balanced because the difference of left and right is 1. Now coming one level up, you see this node which I am marking is not balanced because the left height of this node is 2. There are 2 levels to the left of this node and 0 levels on the right. Minus 0 is 2. So the node here is not balanced. Okay. Then it is enough. No need of checking other nodes. The tree is unbalanced because even if a single node disobeys the rule, then the entire tree is unbalanced. And most importantly, the node which is not balanced from the bottom is the node which I have marked as X. Now, what happens most of the times, would claim some other node that it is not balanced. Like if you see, root is also not balanced. Correct? I'm marking the root. It's very easily seen that the left height of root is 1, 2, 3, 4, and the right height of just 1. Observe. So 4 minus 1 is 3. So you may say root is not balanced. Yes, I agree root is not balanced. But the first node you have to find out from the bottom, which is not balanced. That's very important. And the first node from the bottom, which is not balanced, is the node which I have marked as X. The node which I am encircling now. This is the culprit. Correct? All right. We have seen enough. Now let's come to these pictures which I have drawn here. Now this is an example. Example tree is an AVL tree. What do you mean by AVL tree? Balanced. Yes. This tree is balanced really. Or really is it balanced? If you note the cursor position now from the bottom level, 4 is balanced because left height minus right height for 4 is 0. Correct? 5 is balanced because difference between left and right for 5 is 1. 11 is balanced. Correct? 0 minus 0. 17 is balanced. 0 minus 0. Come up by one level. 8. Now the left height of 8 is 2. 2 levels on the left. And right height of 8 is just 1. So 2 minus 1 is 1, which is allowed. Now 18 is balanced. 18 is balanced because left height is just 1, right height is 0. So difference is 1. And finally this 12, the root. See the left height. Left height is 1, 2, 3. The right height is just 2, isn't it? So 3 minus 2, which is 1. So all nodes are obeying the rule, correct? So hence we can say this tree is balanced. Whereas this tree is not balanced, observe. Tree is not balanced because if you check from bottom level, 2 is balanced, 4 is balanced, 1 minus 0 is allowed, 7 is balanced, come one level up now, check these nodes, one level up. 5 is also balanced because the left height is 2, 2 levels on the left and just one level on the right. So it is balanced, 2 minus 1. 11 is perfectly balanced, 0 minus 0. 17 is balanced. 0 minus 0 again for 17. But 8 is not balanced, you see. Why 8 is not balanced? 8 is not balanced because if you see the left height of 8 is 1, 2, 3 levels. And right height of 8 is just 1. So 3 minus 1, 2, which is larger than 1. So 8 is not balanced. And actually it is enough. You can stop here, say declaring that the tree is not balanced. But if you really want to continue, you can say 12 is also not balanced. And obvious, it will be. 12 is not balanced. Because if you see left height of 12 now is 1, 2, 3, 4. And right height of 12 is 2. Minus 2, difference is 2, which is not allowed. So 12 is also not balanced. Hence, the above tree is not balanced because difference between left subtree and right subtree of 8 and 12 is greater than 1. So in this video, we have seen AVL tree is same as binary search tree. But how do you know whether the tree is balanced or not? What do you mean by the rule HL minus HR should be less than or equal to 1? How do you find out the first culprit, the first node which spoils the show? and that has to be checked from the bottom level. You have to find out the first node from the bottom level which is spoiling the rule. Okay, see you in the next video where I will tell you mutation algorithms, very interesting, and how AVL solves these cases of unbalancing. Thank you very much.